This presentation will start in approximately 3 minutes' time. Welcome to this presentation on Hydro International by Hydro International. The subject which is getting the highest flow through the smallest footprint. My name is Philip Taylor. I'm Hydro International's product specialist for stormwater products. My contact details are on the screen there, and they'll go out probably after this with an email that will follow up with contact details and the like that you can follow up on. If you have any questions throughout the presentation, you can try typing them into the questions section of the control panel, and I will try to address those at the end of the webinar if we've got time. We should be doing probably about 35 minutes for this presentation. If I can just work out how to advance the next slide, we'll be even better off. Just one moment. I seem to have a technology glitch here. I'm not getting the slides to advance. So just give me a second to try and sort this out. Okay. Just had to click in the right spot on the screen. For those of you that need them, certificates of for continuing education will be sent out. Those will go out automatically, probably next week. The person that does all that is away this week, and she'll send those out next week. Just a run through of the material for this presentation. First of all, I'm going to just introduce Hydro International, then talk about some prizes that will be presented and available at the end of this presentation. I'm going to do a couple of polls along the way. I'm going to talk about vortex separation, and talk about what influences sizing, and then a little bit about the first defense high capacity end with a follow-up poll as well. The origin of the stormwater treatment industry as we know it in terms of the vortex separators goes back a long way. It goes back to the mid to early 1960s. Hydro International, one of their founding fathers, developed the vortex flow control valve, and it's basically from that technology that all the vortex separators have developed over the years. You can see here some early photos of his research lab in the front room of his house in the United Kingdom. From that, Hydro International has grown into an international company. We do work in about 33 countries at the moment and employ about 140 or so people. So in that 30 years plus experience, we have installed thousands of separators and filters across the country and worldwide. And we're fortunate that Hydro International has a manufacturer-owned hydraulics lab, and it's one of the largest and best equipped in the country. So we can do a lot of testing and experimentation within our own facilities. This helps us develop products quickly and also to understand the industry and other products. So it was this, Hydro International itself was established formally in 1979, and we specialize in stormwater, wastewater, combined sewer overflows. We partner with a lot of universities and technology companies to develop our research, as well as we do a lot of work with the approval agencies, DOTs, ministries of environments to ensure that the products are certified and approved for use. Now at the end of this presentation there will be a short follow-up survey which we'd like you to fill in. At the end of that survey there will be a skills test, basically a question there, and if you answer that question you'll go into the draw, and we'll send out to 10 lucky people a stainless steel double-walled hydro travel mug. In one of those mugs will be a $50 Amazon gift voucher. So good little prize to have if you just do the survey afterwards and answer the skills question. The mugs are really good. I know they're good because my wife stole mine. So she only steals good stuff. So we're going to go into a poll now. Just run this first poll. And I'm just going to bring that poll up. Just want a bit of feedback to get an understanding of the audience and what your understanding of vortex technology is. So I'm going to run this poll. And if you could fill that in quickly, this will give us some feedback. Just a few more seconds here. We've got about 75% people voting at the moment. Before I close the poll. We've got a fairly good vote rate. We've got about 81% voted now. A couple more seconds and I'll close the poll. I don't think the results are going to change much, so here we go. Close the poll. And let's see, if technology works, you should see the results. And here we go. So we see about 75% roughly people have a basic understanding. Very few people have a detailed understanding of these products, and quite a large percentage there, 22% of you have a, this is new to you and you're going to be learning a little bit. I was kind of considering that when I was putting this together. I wanted to give people a good understanding of the technology that we're working with. So I'm going to talk a little bit now about vortex separation, give you some background on how these products work and their application. So if we look at, there's actually two ways these products work. There's two functions. One, you want them to remove sediment, trash, maybe some oils, but primarily sediment is their primary design pollutant. But you also want them to retain that under different flow conditions. So you have a removal function, and you can test for that, and you have a retention function, and we test for that as well. I'm going to try and run this video here. Hopefully it'll come through. Now, what you're looking at here is a standard sort of sumped manhole where the water comes in from one side, flows out the other. There's no special flow regimes. This is typical of a vortex, not a vortex, a sumped manhole that a DOT might use or a local authority might use as a gross pollutant trap. And during high flow events, these systems, even though they might remove something under low flow, because Stokes' law will remove something, under a low flow condition, under a high flow condition, they generally wash out through turbulence. And that's the result there. We see that we start with a full container of water and some tracer dye in there. In the end, we end up with no sediment and no water. And that's pretty common. And so the vortex separators have all been designed to improve on this situation and try and make things better. Now, if you were to do one thing, and this is a bit of a freebie, if you were to do one thing and take the inlet pipe and bring it in at an angle so that you create a swirl, just like stirring a cup of water or just stirring something up with a little spoon, you'll find that you'll actually change the whole situation dramatically. And by that I mean, instead of washing out 100%, you'll actually have some material left. So these tests are actually done, and papers have been written on these. We partnered with the John Moores University in the UK to do these. They're mimicking about a 75 to 100 micron particle size and settling velocity. And you can see here that even after going through the same flow regime as the first test, this material is retained within the container. So we've got some retention. Now that's just by changing the inlet pipe. So if you were doing a sumped manhole, the logical thing to do would be to bring that inlet pipe in at an angle, and that would improve water quality straight away. But really what we're trying to do is go beyond that. We really want to improve the retention and the removal as a combined function of that structure. And this is a video of the downstream defender. This is a product by Hydro International. In this case, we're going to show water coming in, bringing with it sediment. Now, this is about 10 minutes of flow sped up to about 30, 40 seconds here. And you can see the material coming in, settling out, being separated. And the whole purpose of the internal components is to try and control the flow and direct high velocity flows away from the sediment to do the removal of trash, removal of oils, removal of sediment. You're asking it to do a lot in one little container. And when we get the high flow come through, we want to keep everything in there. Now the downstream defender does this very well, but it does it by compromising other things. Because it's not only the function of the device that you've got to design for, you've also got to design for the application of the device in the real world. So you can design the perfect system, but no one will use it because they can't shoehorn it into what they're really trying to do in the real world. So that's a little bit about the vortex separation. The technology does work, but in order to make the perfect system, you have to compromise a few things, so to speak. So now I'm going to just cover a little bit about sedimentation, rain, and vortex sizing, because in this industry, when we're talking manufactured system, everyone's trying to sort of get the most out of the least. They want the smallest footprint, they want the lowest cost, but they want the highest performance. So that's one of those compromises that we're trying to do. So let's look at the conditions that we're working under. So when we're talking about vortex separators and pollution removal, back in, I think this was sometime in the early or mid-80s, 90s, like that, there was a lot of work done into trying to decide what exactly was washing off streets and off parking lots and off buildings, and what it looked like. That was the NERP studies, the North American, I think, Urban Runoff, or the Nationwide Urban Runoff Program, which was funded by the EPA. And they looked at lots of different sites, did lots of measurements to try and decide what was actually washing off. And if we look at things like the parking lots, streets, roofs, and mixed use, which is typically the smaller sites that we see these separators used for, there's quite a bit of information produced. And they looked at these and they did lots of measurements of the particle size distribution that was coming off to try and define what that TSS was. We see here for a parking lot, they ended up with an average curve there. For roof areas, for collector streets, feeder streets, arterial roads. So there was a lot of data collected, mixed use, and that ended up with a series of curves called the NERP curves. And these have been applied in the design of stormwater standards around the country. But what we find is when we look at them, we want to try and normalize things a little bit. So if we look at the median particle size, and that's the particle size which 50% of the material is larger and 50% of the material is smaller, it gives us some idea of the fineness of the overall particle size distribution. You find mixed use, generally, it's a 42 micron particle, D50. Parking lots, somewhere around 52 microns. Collector streets, looking around about 70 microns. So there's some similarity there, although when it comes to Stokes' law and settling, there's quite a lot of difference between the settling velocities of these particle sizes. And then when you get down to arterial roads, institutional, it gets larger there. We've got 90 microns, and feeder streets, quite coarse, 200 plus microns. So you're starting to look at the sand to coarser sand, and ranging from coarse silts to very fine sands at this mixed use level. So we have that information. And when we look at, perhaps one of the test things to look at is the New Jersey Department of Environmental Protection. The New Jersey DEP has a test blend that we have to test our equipment with, and the particle size distribution is shown here. And the average particle size, or the median particle size is around 63 to 70 microns. So it's something similar to what the NERP study showed. Has a lot of very fine material in it though, and some coarser material, but it is quite heavily weighted with fine material, making this a very tough material to remove with manufactured systems. So we have data for this. Now, what we did with, when we did our testing on our equipment, I don't know if many other manufacturers have done this, we actually measured discrete particle sizes coming in and coming out of the device. So because we're putting all this material through there, we thought it'd be a good idea to look at what particle sizes were affected by our device and how well they were removed, and where the device started to struggle. And what we found is when we looked at the banding from, say, if we looked at 1,000 to 500 microns here, we removed about 100% of all that material. And it's not hard, it's pretty coarse, pretty heavy material, it settles very quickly, so no surprises there. When we look at the 500 to 250 band, we're probably looking about 96, 97% removal, and so forth, going down 150 down to 100, about 80%. Interestingly, when we get down to the 50 micron, or around the 75, 50 micron, that's when we see things change dramatically. In fact, from 75 to 50, there's a big step. And this is for the downstream defender. We found, you drop from 81%, suddenly you're down to 21%. So somewhere around the 50 micron range, the particle's getting light enough and small enough that it's really bouncing around in the flow, and it's getting very difficult to remove. And it's very sudden when that happens. But in line with what we're looking at in terms of the TSS coming off from the NERP studies, we need the target somewhere around a D50 of these 75, 50 microns. But if we look at just that whole band from 1,000 down to about 50 microns, our overall performance is probably around 85 to 90% for that range of particle sizes if that was a complete set itself. So that's pretty good performance. Now that's just one piece of equipment. We did the same thing with the first offense when we put it through the New Jersey test protocols. And interestingly enough, we had correlation. So when we did the same series of tests and we looked at all the particle sizes, we actually found the first offense was doing a bit better. Down to about 150 microns, we were removing almost 100% of the material. And when we got down to the range of the 75 to 50 microns, again, it was doing better. But again, we saw once you drop below 50 microns, the performance of these separators is really difficult to get them to remove that fine material. And in fact, once you start dropping down to 20 microns, filtration struggles with this as well. And just as an aside, prior to the current protocols for New Jersey, there are a lot of media filters approved in New Jersey, and recently New Jersey changed the test protocols and put everyone on a lab test standard and put everyone through the same testing. Everyone had to switch to a membrane filter in order to pass the test because they needed to remove a lot of material that was below 20 microns to pass the test. And a lot of media filters will fail that test, so you need a membrane filter to actually strain out those very fine particles. But again, we have correlation between the two pieces of equipment that somewhere around 75 to 50 microns is about where they're starting to bottom out performance. But to that point, they're doing pretty good. So again, if we take that whole band from 1,000 down to about 50 microns, your removal is well north of 80, 90%, so good correlation. And we can take it one step further because we can go out into the field and just scoop some of the material out of the sump that's been captured and retained and just take a look at that. And this represents a range of vendors and a number of different tests. We can see that the D50 is ranging from below 10 microns here, it's 0.01 millimeters. Sorry. Up to about 150, 200, 300 microns. So that would reflect maybe some of the source area as well. But it also reflects that maybe these pieces of equipment that have this finer material in are more resistant to washout. They're better controlling the peak flows. But we do again get this correlation that material we're collecting is pretty fine. So what do we do with this information? If A is equal to B and B is equal to C, is A equal to C? In this case, I think it kind of is. We've got TSS coming off sites with a D50 in the range of 50 to 200 micron from the studies, from the NERP studies. We've got, within our own company, validated test data that shows that we're getting very good removal down to about 50 microns. We have sump data showing that we're retaining material in the 20, 10 micron range, which is pretty good. So vortex separators probably do work as intended, and they're probably quite fit for purpose. So it's good when you get that sort of correlation and confirmation. So if we look at vortex separators in general, where do they sit in the whole toolbox? When we look at the range of pollutants that we're trying to remove, you start with the gross solids, sort of greater than 1 millimeter. You're really looking at screening systems. When you're looking at trash and debris, those are the gross solid stuff, that's screenings. Some vortex separators are doing pretty well down to the sort of 100 microns. Your advanced and better designed vortex separators will get down to maybe 50, perhaps even, if the flows are right, 20 microns, but that's really stretching it, more suited to ponds perhaps. And then when you go below 20 microns, you've really got to go with filtration systems, bioinfiltration systems, green roofs, large ponds, that sort of stuff. So it's very much a horses for courses thing, and also maybe possibly treatment train systems to address the pollutant runoff. So we have confidence that these things work, but there's another side of this equation. You've got to size them appropriately for the site. So that's a big question mark. Is the system appropriately sized? Now, there are two primary sizing methods within vortex separators within the industry. One's known as the net or average annual method. Now, this is baked into a lot of stormwater manuals. You'll often see must be sized on an average annual basis, written into many stormwater manuals that address manufactured systems. I have a few concerns about that, and I'll explain how the method works. Basically what you do is you take a long-term rainfall record and either create a synthetic annual rainfall record from that, or you run the historic data and average it, but you end up with basically a banding that says, okay, a certain percentage of my rainfall has this intensity. A certain percentage of my rainfall has that intensity, and so on and so forth, and you can band the intensities over a long period of time. So basically you end up with low intensity, high frequency, those are your everyday sort of rainstorms, to your high intensity, low frequency, big gully washing storms, and you can band those out and you can give them a percentage of the distribution. So now I can then say, well, if I install my device in the field, it's going to see a lot of low intensity storms which have a high level of frequency, and I know on my removal for that intensity, I can translate that into a flow rate using the rational method, and I can just weight my removal and say, okay, the first level of intensity gives me that flow rate. It accounts for, say, 30% of the storms. I'm 99% efficient at that flow rate, so 30 by 99 gives me 29% TSS reduction for that band of storms. And I can carry this banding calculation all the way through and sum them all up and say, okay, on an average annual basis, I can remove, say, 80%. The problem with that is it doesn't really account for, or I should say it accounts for removal with every storm. Now, a lot of these storms, especially these very small storms, high frequency storms, may not be sufficiently powerful enough to mobilize and transport sediment. So even though I'm claiming credit for the removal in the calculation, I have a question whether that material actually moved on site and got into the system. But because I can size it, it's weighted towards these small storms, I end up with a smaller system overall. So there's some question in my mind whether this system really correlates to the storm which actually moves the pollutant. Okay, so it's a valid method of sizing. I think it just needs more study, and it is baked into a lot of stormwater manuals. Now, the other method of sizing is to take your water quality event. Now, this method is also often baked into the same stormwater manual, and it's often known as the water quality volume or the water quality capture volume. And in this sizing method, you take a single event and you work out the peak runoff from that event and size the equipment based on that. Now, this is more conservative because it takes a peak runoff rather than an averaged annualized runoff. And if you were looking at many regulations, they might say you have to treat the first 1 inch or ½ inch of rainfall that falls on the impervious surface, and that ends up with a water quality volume that you've got to put into a holding system and settle out the sediment from that. So in our system, we would then convert that water quality volume into an equivalent runoff rate and treat that as continuous runoff rate. So our equipment is sized to remove 80% at that peak runoff, but it's removing greater than 80%, anything less than that. So it's a conservative way of sizing. It's a good way of sizing. I personally prefer it, as it's a more conservative system. And you can then know that regardless of the annualized rainfall pattern, when you hit a certain intensity, your size for that intensity, it's more likely that the runoff from that intensity will be the first flush that is actually carrying the majority of the pollutant load. Okay, so I'm going to run a second poll here, just get your feel on how you're feeling about the presentation and your understanding of your local regulations. So I'm just going to run the second poll. If you wouldn't mind helping me out here, just throwing a few votes on your screen. This is also my plan to keep you engaged so that you're not falling asleep or wandering off and doing other things while I'm talking. You've got to rush back to the computer now and push a couple of buttons. Okay, we're getting a good response here. Okay, I think we've got a majority of people voted now, so I'm going to close the poll in about 5 seconds. Okay, I'm closing the poll now, so we'll just take a look at the results because I don't think they're going to change much in trend. So interestingly, 56% of you say, yep, you can use them as part of as a standalone or part of a treatment train. Only roughly 3% believe they're not allowed in your area. 30% of you think it may be if certain conditions are met, and this is a common thing we get with some areas where more conservative design says, well, you can use them as a last resort because we don't want to go underground. And 10% of you, which is a fairly low number, not too bad, don't know your local regulations on the subject. But, so that's not bad result there. So one thing I want to go through now is the sizing side of things and the pre-approval and regulation side a little bit on that, and we'll almost be through this. One thing that's really important with these devices is it's easy for me to come up with an idea and pitch that out there and make claims, and we see this all the time. You know, it's the greatest thing since sliced bread. And of course, you can't say it's not because you don't have anything to compare it against. So there are two main clearinghouses currently in operation. One is the New Jersey Department of Environmental Protection, the NJDEP test protocol, known as the TARP protocol. That's a whole different presentation in itself. And on the West Coast, we have Washington DOE using the TAPE protocol, which is more of the main difference between the two is that the Washington test protocol is a field test protocol, and the New Jersey protocol is a lab test protocol, and they're significantly different because of the variability between field testing and lab testing. So most people head off to the East Coast, to New Jersey first, because it's a lab-based test. It's faster to get through, and everything's standardized to very similar protocols, which makes it easy to compare. So the game that we have to play here when we turn up with our new devices, that we're really trying to beat everyone to the finish line, so to speak. Normally we test a full-size piece of equipment, and that's usually a minimum. It's a 4-foot diameter manhole, and when you go into this, you have to state what your treatment flow rate is, and then do the test protocols and prove that at your stated treatment flow rate you achieve at least 50% TSS removal on a weighted calculation that New Jersey uses. It's not a direct measure of removal, it's a weighted calculation, and that's, I say, it's a whole different presentation, but you have to meet your mark or you fail. So the you turn up and say, okay, I've got a 4-foot manhole and I've done some pre-testing, so I'm going to state, and I might, 1.5 or 1.4 is my treatment flow rate that I want to be approved for. And all these yellow highlighted boxes are the tested units and basically the stated flow rates. And so we see that they're very similar in many ways. 1.12 for the downstream defender, 1.5 for the 4-foot first defense high capacity unit, and that's the highest approved flow rate for any device currently on the NJDEP approval list. CDS about 0.93, Aquasoil for 1.18, Vortex, StormPro V48, another 4-foot unit, 1.29. So we get similar sort of flow rates. Now you think, okay, if everything's so similar, what's the difference between them? Well, what kicks in is scaling. This is the tested unit. So when you start to scale for the real world, sorry, I don't know if I might have forgot to turn off the poll, so hopefully you can see what I'm talking about now. When you start to scale for the real world, you have a significant change take place. Now, the scaling for New Jersey is what they call surface area rate scaling. So it's just it's a scaling of a factor of 2. So you just take the load rate for the tested unit and apply that load rate to any other unit, and that's your flow rate based on the area. So it's an area scaling. So when I take my test unit, say the 4-foot first defense here, and I got approved at 1.5 CFS, we scale to the next one, 5-foot, and I get 2.3. Now it's the same surface load rate, so it's working at the same rate, but I get approved for 2.35, and I get to my 6-foot unit, I get to 3.38, and I get to the 8-foot, and I get to 6 CFS. So these become my approved flow rates for my different size units. And we start to compare that to how the scaling affects when we look at, say, an 8-foot FD unit here, FDHC, 8-foot CDS. It makes a significant difference at 3.7, Aquasoil 3.4. When you start scaling from a small difference in the test unit, that small difference really kicks in when you start looking at scaling up to these units that get used on larger projects, so that the footprint size, for instance, if I was to use a 4-foot an 8-foot FDHC at 6 CFS, the equivalent would be an 11-foot Aquasoil. So that's where, in the commercial world, that these the ability to get a high treatment flow rate in your test unit and get approved is quite important, and that's sort of something the industry you really are trying to design the highest flow through the smallest footprint. That's the whole theme of the presentation, that we're trying to squeeze as much performance on the very small units. It's tricky because we have to look at the real world as well. So if we take the first defense high capacity unit and we look at, okay, you've got this unit that really wants to perform well, it's approved well, but can I shoehorn it into my site? And that's where you have to look at all the compromises when you develop these products. And the first defense, we worked really hard to get this thing to work well on sites, as well as get the approved flow rates. And it has a double bypass. It has a large center opening to allow maintenance. That's something that's really important in the industry, is maintenance. If you make it hard to maintain, they're probably not going to do it, or whoever owns it is going to think, well, this is the wrong thing for my site if I can't maintain it. So that's an important part of water quality, is that these things must be maintained. It's like all things. You don't maintain it, you're wasting your time. So it's designed for sediment removal from the very fine sand, maybe coarse silts and larger. We designed it to treat at high flows. Now, hydrocarbons and trash and floatables. Now, this is where you start compromising your design a little bit, because these things are floating and not settling. So you've got the top part of the unit that you're wanting to get the flows through and get your bypass in, but that's where your hydrocarbons and trash and floatables want to sit as well. And then the bottom part of the unit is where you're trying to protect and get your sediments. So Some of these units aren't so good. The first defense is okay for hydrocarbons and a little bit for trash, but all internal bypassing units really compromise the hydrocarbons and trash removal in order to accommodate more real-world installations where you're trying to get pipes in, you're trying to get peak flows through, and you're trying to shoehorn into a site which might be tight and difficult. So the first defense, we spend a lot of time getting our verifications, certifications, and approvals. As part of that, people often ask us, why is a 4-foot manhole, which costs maybe a few $100s down at the precast, or with some plastic in it, suddenly costing $10,000, $12,000, or $50,000 for a really big one? And the answer is, well, the actual manhole and the plastics are quite cheap, but we have to fork out about $500,000 to $1 million up front before we get approval to sell it. And in some cases, you even fail at that, so you have to go back to square one and start again. So the cost of entry into this industry is really high, and that's where that cost of these products is really set from. So in shoehorning this into a site, the real world is an engineer has a certain pipe layout. He's got a building in one corner, he's got a parking lot, it's got services, pipes have to go left here, they've got to go right there, they've got to pick up water from over that point and then discharge at some other point. So it's better that the system can adapt to the site than rather trying to adapt the site to the system. And the first defense allows that by having the bypass wears are set at about 135 degrees. You can put your outlet pipe anywhere within there, and then you can have your multiple inlet pipes coming in at different angles and at different heights. So that makes it a very flexible system, and they can be different size pipes. You want to make it contractor proof as well, because what we need to do is allow for people who are used to just slamming manholes in the ground, and you're never sure exactly how good the people are that they're employing, or whether they're under pressure to get things done quickly, what materials they're using. So the first defense is fairly robust. The contractor doesn't have to do anything. It's fully assembled when he gets to the site. It looks like a manhole and it installs like a manhole. And even if they put it in backwards, because it's actually symmetrical in its design, the only difference between back and front really is the angle of the wears. The water could flow either way. It will still work. So even if you have a backflow condition, where you're cycling water from one point and maybe pushing it the other way at another time, and that does occasionally happen, it will still do the same job because of the way it's designed. We have the inlet and the outlet chutes mirror images of each other, and so the water can flow either way through them. It'll still operate the same. As I said, maintenance, it's a simple maintenance procedure. Down through the top, just vector it out. Maybe a bit of jetting, simple thing to do. And for the industry, there's often requirements for different sizing standards. Even though we've done the NJDEP testing using one particle size, we're able to pull performance data out of that for different particle sizes as well. So we have verified test data for 50 micron, 110 micron, and 150 micron particle sizes. And that accounts for much of the industry. 110 micron is a very common particle size used by a lot of regulators, such as the City of Indianapolis, for sizing their equipment. So it's a fairly standard one. We can give performance curves for all these, so you can actually just pick a different level of performance. We actually have online sizing tools as well. In a follow-up email, you'll get links to all this as well, so you don't have to worry about trying to copy all this down now. Our online sizing tool, we're updating it currently. You can size by particle size, and you can size by regulatory area as well. We have backup with sizing tables, which makes it easy, where you can just pick a table and pick your treatment flow rate, your particle size, peak flow rate, and just pick a unit straight off a table. Okay, so in summary, vortex separators, they have an application. They're good technology, especially the more current ones that you're seeing on NJDEP. They've been through some very rigorous testing, so you can rely on that testing. It is good level testing. Everyone's been through the same protocols, the same test material, the same text reviewers. So the new NJDEP website is a great place to reference things. They do certify for 50% removal, which is a weighted removal calculation, and we can show maybe how to get that to 80% removal for people who say, well, I need 80% removal. Talk to us about that. We can show you why that's still applicable. And we need to educate many people and end users on maintenance. This is a key area. Hydro has its own maintenance division now, but unless you're cleaning these things and looking after them, once they fill up, they stop working. So maintenance is a key part of the future of stormwater. I'm going to run the last poll for you now, if you just don't mind. This is the last poll and pretty much the end of the presentation. And if I've done my job right, people should be feeling fairly good about the technology. Excellent. Thank you for voting here. I'm just going to close the poll in a couple more minutes. Sorry, a couple more seconds. I don't hang on that long. Okay. Closing the poll now. I'm going to share it with you. And it looks like, well, the vast majority of you feel good about the technology, which is good. A few of you have a situation where local regulations prevent easy use of the technology, and that's something we try and address with the local regulators and go and talk to them. If you have someone locally that you're having trouble with who you'd like us to talk to, we do that as well, so we can come along and present a logical argument sometimes and get things approved that might be difficult to get approved otherwise. And that's pretty much the end of the presentation. I want to thank you for your time. I know it's been about 45 minutes now. It's plenty long enough for you to be online. When this presentation closes, there will be a follow-up poll, and as I say, there's a competition in there, a little prize giving at the end of it. So I'm going to close the presentation now. Thank you for your time, and please do the follow-up survey. Thank you very much.